Hello, everyone. I'm JC Jones, and I'm joined here by Tim Geoghegan. We're both engineers at the Internet Security Research Group, which you probably know as the public benefit nonprofit that runs Let's Encrypt, where we actually operate Divvi Up, a production deployment of the IETF Distributed Aggregation Protocol for privacy-preserving measurement. So today we're going to show you that multi-party computation isn't just a research curiosity anymore. It is actually running at internet scale, processing billions of contributions from real users in applications like Firefox. So organizations, as we all know, need telemetry to improve their products, things like how fast the pages load, which features get used, the rates of error. Traditionally, that means that you're collecting raw data on a central server. But even with good intentions, we here all know that is a privacy risk because that server sees every individual measurement and where it came from. Multi-party computation has promised a way out for decades, but real-world deployments have been vanishingly rare. The Distributed Aggregation Protocol, DAP, changes that. It's an IETF standard, not a research prototype, designed from the ground up for production deployment. With DAP, clients split their measurements into secret shares and then send them to 2 independent servers. And neither server can reconstruct any individual's data. The only thing that comes out of the other end is the aggregate. You know, a sum, a histogram, a count, never an individual contribution. Privacy is one of DAP's 2 core goals, and the 2-server model is how the protocol delivers it. Like I said, clients split their measurement into 2 secret shares. One goes to the leader, the other goes to the helper. And these servers are run by different organizations. We'll specifically talk about our deployment with Mozilla today, where ISRG operates the leader through our service Divvi Up, and Mozilla operates the helper themselves. So neither share reveals anything about the original measurement. The only way to recover an individual value would be for the 2 servers to collude. And because they're run by separate organizations with independent infrastructure, independent incentives, and oversight, that becomes a meaningful trust boundary. So, then the question comes up, why not 3 servers? Why not 4? And more parties would raise the collusion bar further, and that is a real benefit. But going from 2 independent organizations must conspire to 3 must conspire, it's a modest privacy gain for a significant jump in cost and complexity, because every additional server means more network round trips, another organization to coordinate with. So 2 gives you the privacy property that you're looking for with a system that you can actually deploy and operate at scale. So the aggregation flow, it happens in 3 phases. First, you upload. The clients encode that measurement that you're looking for with a VDAF, Verifiable Distributed Aggregation Function, VDAF. And then they upload the secret shares to the leader. This is a lightweight encoding. For histograms and counters, it is sub-millisecond, even on constrained devices and mobile browsers. Like, this was designed explicitly to run on the web platform with things that are already in your pocket. Next, you aggregate. So the leader and the helper jointly verify that the shares that they've received represent a valid measurement. That's the verifiable, the V part of VDAF. The servers can reject malformed inputs without ever actually seeing the underlying data. And then they aggregate and combine the valid shares. And so third, only we collect only that final aggregate, the sum, the count, the histogram, only that is ever reconstructed. No individual contribution ever gets revealed. So a critical point of operating this at scale is, of course, automation. We manage batch life cycles, right? Collection windows, aggregation scheduling, all the result delivery entirely through automated pipelines. As we've well learned operating Let's Encrypt, you can't run billions of contributions through anything that requires manual intervention, certainly not with a small team, right? So if MPC has been around for decades, why hasn't it been practically deployed? First, general purpose MPC protocols are computationally expensive, right? They're just too expensive for high volume telemetry that you actually want to use this stuff for. The VDAFs here, the verifiable distributed aggregation functions again, of which DAP implements several, they solve this by specializing in the aggregation that they do. They are not general purpose. They don't try to compute arbitrary functions. They just compute sums and histograms, and they do it fast. Secondly, prior deployments typically required a cryptographer to design and validate every configuration. DAP standardizes that. It defines safe configurations for the common measurement types. So your data science and privacy engineering teams can deploy this without needing to make cryptographic design decisions. And then, there's the third kind of obvious elephant in the room operational problem. Where do you find an independent party, an actual independent party that's willing to operate the other server and you trust to operate it at the scale you want to run at, right? Divvi Up does exist to answer that question. You run one aggregator, we run the other.
All right, so we're making a lot of very bold claims here about what a big deal this is. So you might quite naturally ask, does it actually work? Well, yeah, we would sure like to think so. Divvi Up is our DAP aggregator as a service, and it's been available in production for over 3 years. In that time, we've processed billions of reports and routinely burst to rates of over 450 million per week. Point being, that's more than enough capacity to aggregate telemetry from quite large cohorts of users. The infrastructure in use here is not exotic. USENIX, which is our implementation of the aggregator, is a very standard Rust web service, and it runs on commodity cloud infrastructure. This is not a bespoke research setup. This does not require constant attention from a legion of PhD students. It's production software running on the same kind of extremely boring infrastructure that you would use for any scalable web service. One of our major deployments has been in partnership with Mozilla Firefox. Firefox has always had strict rules against collecting any data that would reveal to Mozilla, even indirectly, the websites that a user visits. Now, this has always put them at a disadvantage relative to some browsers that indiscriminately scoop up sensitive data of that nature. In partnership with Divvi Up, though, Firefox can record telemetry that previously would not have been safely accessible, while providing strong and publicly verifiable guarantees that nobody off-device could learn what the user is doing online. Now, none of this is exclusive to Firefox, nor is it particularly tightly coupled to their use cases. The system here is general purpose for telemetry. Any application that needs privacy-preserving measurement can make use of DAP. Now, obviously, adding all this math and all the zero-knowledge proofs is going to make this more expensive to run as compared to what you might call a conventional telemetry pipeline. But you might be surprised to learn that the costs aren't higher, given that, again, this enables measuring telemetry that would otherwise simply be too sensitive to consider gathering. So what we have here is a breakdown of what it would cost to run an aggregator that scales to about 100 million reports processed per week on Amazon Web Services. So the costs are primarily dominated by storage, a managed SQL database. Data transfer being also significant, but a distant second. And I want to underline here that all of this is on commodity hardware or pretty basic cloud products, right? You don't need any fancy hardware accelerations, you don't need any specialized coprocessors, and you don't need to reach for your cloud vendors' confidential compute products. This is EC2 virtual machines and managed Postgres. Now, let's talk about how we might compose privacy technologies together to achieve even stronger privacy goals. So in particular, the MPC that we've been discussing protects the privacy of individual contributions, but aggregate results can still leak information. So for instance, if what you're doing is constructing a histogram where each bucket represents an error that your software might encounter in the field, and then suppose further that one particular bucket, one error code is extremely rare. It only occurs 0 or 1 times in a given batch. Now you might use DAP to privately aggregate over all of this, but that count of 1 does not provide much cover for the user who encountered that outlier error. So this is where you'd apply differential privacy, right? I think as this room understands pretty well, we can add calibrated noise so that you can't meaningfully distinguish between a 0 or 1 in that bucket. A further layer we might add is oblivious HTTP, or OHTTP. Now, even with secret shared measurements, the leader still gets to learn at the time of the client uploading various pieces of identifying metadata like an IP address, a user agent header, the time at which they uploaded, stuff like that. But if you route those uploads through a further relay server using OHTTP or whatever anonymizing proxy you like, then the leader can no longer link contributions to participants and find out who is contributing telemetry at all. And DAP was designed to compose gracefully with all of these things. So the picture that emerges is one where DAP gives you input privacy. No server, indeed no protocol participant except for the client, ever sees individual contributions in the clear. Differential privacy gives you what we might call output privacy. Now we can have strong bounds on the amount of information leaked by the aggregates that come out of the pipeline. And OHTTP gives you metadata privacy. So the servers no longer get to learn who is participating in aggregations. Now all of this, of course, comes with some trade-offs. DP in particular means you're going to have to think really hard about privacy budgets and query planning, right? You can't run unlimited queries on the same piece of data, or sorry, same set of data, without eroding privacy guarantees. So this will have a big effect on your experiment design. You need to make sure you have enough contributions per batch to get useful signal through the noise, but also to have a big enough anonymity set to protect the privacy of participants. Okay, so perhaps all this theory is sound, but practically speaking, how might you start using this? Well, first off, the implementations for all the protocol roles are open source and permissively licensed. USENIX is our implementation of the aggregation server, written in Rust, and it's up on GitHub. So you could build it yourself from source, or use the container images that we distribute and run it in your infrastructure. So what you might do is use Divvi Up as a hosted leader service, and then you bring your own helper, and you're up and running and gathering telemetry privately. And for uploading telemetry, we provide client libraries in TypeScript, Rust, and Java. Second, this is all being standardized at the Internet Engineering Task Force, right? This is not a one-off research project. That's going to matter a lot for organizations that need confidence that they're investing in something that has a real future. Interoperability has always been a design goal of this work. Our belief is that high-quality, open standards are a necessary step for aggregator operators besides Divvi Up to emerge, which would provide application owners with more choices when deploying DAP. Third, and this is for all you privacy engineers in the room, you do not also need to be a crypto team to deploy this successfully, right? You can get started by picking a single, a single simple metric, maybe a counter that counts how many users have hit a particular error today. So that counter is one of the VDAFs, those well-defined primitives that are already integrated into DAP. So you reach for that building block, set yourself up a pipeline that works end to end, and then from there you might expand to more metrics. Add more probe points to your systems, more types of metrics. You could do histograms, or you can do all sorts of astonishing things with bit vectors. So long as it's like meaningful to sum these things, you can do really interesting aggregations. And progressively, you add more probe points to more applications, and flesh out your picture of what's going on in your deployments. The barrier to MPC adoption has traditionally been about expertise and infrastructure. DAP and Divvi Up are specifically designed to lower those barriers. If you are capable of instrumenting your applications to send telemetry to some REST endpoint, you can use DAP. To wrap up, practical MPC aggregation is here, it's running at internet scale, and it is ready for your use cases. If you want to learn more, divvyup.org is a great starting point. If you follow one of the links on this slide, we also have a Docker Compose setup where you can run the entire deployment, aggregators, clients, everything, locally on a workstation, do integration testing or try it out. Also, you can find the Distributed Aggregation Protocol and verifiable distributed aggregation function specifications up on the IETF data tracker. And the code for all of this is up on GitHub. We would love to talk to all of you about how DAP could be used in your applications or your systems, whether you wind up using Divvi Up or some completely other pair of aggregators. And the Privacy Preserving Measurement Working Group at the IETF can always use more help, especially from privacy specialists, to help us close the remaining gaps between guarantees offered by cryptographic construction and actual measurement use cases in industry. And with that, we will take some questions. Thanks, everyone.